Hello everyone. We have now here on stage Andrei Bozianu from Certro, and he will speak about detecting drive-by attacks by analyzing malicious JavaScript in big data environments.
Thank you.
Let's welcome him on stage. Yeah.
Thank you, guys. I will get straight to the presentation. I'm not really used to make presentations, but who am I? Let me introduce myself. I'm a cybersecurity researcher for Romania National Center for Cybersecurity Incident Response. I have almost 25 years of experience in security. I'm a computer freak from the days when there was no www, no World Wide Web, just BBS. And malware analysis and anti-malware techniques was one of my first hobbies. It all started when my friends, and me included, encountered the Hive virus back in 1992. Many of you might not remember it, but it was a simple do-nothing virus appending its code to .com files. There was no antivirus, so I had to make one myself. This actually opened the taste for malware analysis. But then I found the polymorphic virus. What is a polymorphic virus? Every offspring, every generation of this virus is encrypted using a new key. Therefore, the code of every new generation is completely different from the parents, so to say. This means that extracting a signature is rather impossible. The only constant thing in a polymorphic virus is the decryption routine, but it's too small to extract a signature. Sometimes even the decryption routine is obfuscated so that it differs from one generation to another, but still there is a way. Heuristic analysis basically relies on the fact that even though a signature cannot be extracted, a polymorphic virus has certain features, like searching for certain files, searching for certain processes to infect, trying to open certain files, copy itself, etc., accessing some system functions. The decryption routine of a polymorphic virus is, in fact, its Achilles heel, because this portion of code is never encrypted, only obfuscated. This means that the code is there, but you have yet to understand what is happening. So basically, it's considered suspicious behavior if a process cycles through large chunks of data, applies transformation on data read, like on a decryption function, and then tries to execute the data that it read. Why do I speak about viruses? My presentation is about drive-by exploitation, because there are quite a few similarities between polymorphic viruses and malicious JavaScript. Virus needs to encrypt its own body in order to avoid detection by antivirus signature scanning. JavaScript needs to obfuscate its own code to avoid detection by next-generation firewalls, UTMs, antivirus scanners, etc. To achieve memory execution, a polymorphic virus has to decrypt its own body, therefore cycle through the encrypted code, apply transformations to that code, execute that code. To infect an user undetected, a cloud web exploit has to do the same. What is a web exploit kit? It's a toolkit that automates the exploitation of client-side vulnerabilities, usually targeting browsers and programs that a website can invoke through the browser. Usually, it gathers information on the victim machine, finds the vulnerabilities, and determines the appropriate exploit, delivers the exploit, which typically silently drives by, installs, downloads and installs and executes a malware. More than 70% of ransomware and banking trojans is delivered either by phishing email containing a link to an URL with a malicious JavaScript, or when a user accesses an URL containing a malicious JavaScript in a legitimate website, or served by a third-party advertisement. Usually, there are 4 stages. We identified 4 stages in drive-by exploitation. The first stage is the contact phase, where the user accesses a compromised website, accesses a spam link, or even a compromised ad might do the same effect. The redirection phase, which is the second phase, the user is actually redirected to the appropriate exploitation server according to his own type of browser, version, etc. In the exploitation phase, the actual exploit takes place, and the control on a victim's computer is taken by the attacker, which normally, in the infection phase, starts to install banking trojans, ransomware, etc. This is how it looked like. Sorry. Here is the contact phase. You see a normal website with a malicious advertisement, or a compromised website, or a spam link. All redirect the user to a traffic direction system, which then sends him to an exploit server kit, which then installs ransomware, banking trojan, or other kind of malware. Our focus is to detect the attacks in the contact phase. The attacks are performed usually by inserting malicious redirects, which could be JavaScript redirects, meta refresh tags, iframes, etc. in the in the HTML code of the page. These are examples how it can be done with JavaScript, with meta refresh, or how an iframe would look like. But signature scanning easily detects malicious redirects. Cyber criminals came with a solution, meaning JavaScript obfuscation. How would an obfuscated JavaScript look? Unobfuscated looks like this. So it's pretty readable. The obfuscated version, I don't know if you can see it here, looks nothing like this. Therefore, it's very hard to extract a signature from this obfuscated code. I'll show you a real-life example of obfuscated JavaScript, which we found in the wild. As you can see, there is nothing that you can decide for certain that there is a malicious redirect going on here. But as soon as we deobfuscate this code, we can clearly see very normal looking JavaScript code. This portion, which I highlighted here, is where the actual redirect takes place. Namely, it creates an element in the HTML page, an iframe, whose size is 1 pixel, display is none, and the source is an external link. This means that when someone will access this page containing this code, they will get redirected to this link, which is an exploit site. Extracting the signature becomes an impossible task. As you can see, the code is very hard to read. All redirects are created on the fly while the HTML is rendered in your browser. Malicious behavior can only be determined by emulating the code. But this process is really time-consuming and not always reliable. Emulating the code can sometimes trigger booby traps, which are put in place by the attacker, especially to deter the analysis. For instance, how I deobfuscated this code, it was rather simple. As you can see, it's calling an eval function here, which I replaced with a print, with the print function, which simply displayed the code for me. But There are some attackers who can redefine the print function inside their script. So when you're calling the print function to display the obfuscated code, it might call their own function, which can, I don't know, do you some damage, depending on the attacker. So the challenge at Romanian National Center for Cybersecurity Incidents, we want to continuously monitor the security level of Romanian websites from the perspective of drive-by attacks. But there are over 372,000 websites needing to be monitored, and ransomware campaigns are at an all-time high. We need very small rates for false negatives, and we need to be very careful with this because false negatives mean that Romanian users are exposed to various types of drive-by attacks. We need to be accurate, clean, and fast. The problems we have, though, is that we have a number of websites, a number of website pages, and an analysis time, which to us, in our circumstances, translates to roughly over 20,000 hours of analysis. If you add an average response time per page for like 3 seconds, you get 51,000 hours of analysis. If we were to analyze every page in a Honey client, we should be analyzing continuously for like 5 years and 89, something like this, almost 6 years. And most websites have more than just 100 pages. And most of websites have higher response times. Therefore, the total duration of our analysis could take much more longer than we expected. Plus, most exploit kits use JavaScript obfuscation, which means that signature scanning fails, which means your favorite next generation firewall will not detect them. Even if your browser is up to date, you are still exposed to zero-day attacks. What is a Honey client? I was talking about Honey clients. A Honey client is a full-featured web browser to visit potentially malicious web pages. The environment in which the browser runs is monitored to determine if the visit resulted in the system being compromised. Basically, it records all the modifications that occur during the visit of a page, such as files created or deleted, registered keys, newly created processes, etc. If any unexpected modification occur, this is considered as a manifestation of an attack, and the corresponding page is flagged as malicious. High interaction client, Honey client, seems to be the solution, but it's not, because they are very time consuming. Firing a single instance could add 3 seconds to 2, 3, 4 seconds to every URL we analyze. But also, which is very, very important, they are detectable and defeatable even from JavaScript. We have found some examples of JavaScript code aimed of detecting if the code is analyzed in a sandbox or in a virtual machine. Basically, they are two types of verifying if you're in a analyzing environment. First, you detect the monitoring environment either by, I don't know, a MAC address or certain files or other signs. Secondly, there is detection evasion. I will start with detection of monitoring environment. I found in Internet Explorer a very nice snippet that would allow the hacker to read the MAC address of the client's machine. The code does this because it uses the connect server method of the SWBM locator to get SWBM services exec query method. It queries the network adapter configuration, the class, to return the properties of the network adapters on the system. and simply iterate through the values and alert if any values matches the VMware OUI. Another method of detecting the analysis environment is relies on the fact that most off-the-shelf sandboxes or honey clients have standard screen resolutions. This can be easily verified in JavaScript with this small snippet of code. Also, there is the possibility of detecting the honey client searching for specific file names. Here, it requests the JavaScript engine to load the source script from the client's local file system. JavaScript did not perform any checks to see if the file requested actually a JavaScript source file. If the file is not in the expected JavaScript format, it throws a JavaScript runtime error. This script can be used even to detect VMware tools. The second method of attacking the analysis environment is delayed exploitation. And this can be achieved through event-triggered exploitation, like using certain JavaScript methods that would require a certain environment. For instance, if you put the mouse prompter in a certain area of the screen, or if you click on that certain area of the screen, or if you leave that certain area of the screen. Also, there is a method that adds some sleep time before exploitation, as most sandboxes and honey clients have a limited time for analysis, like a few seconds. If nothing happens, they say everything is okay. But in fact, this code waits more than a sandbox to execute its malevolent payload. Also, there is something what I call selective exploitation. The attacker decides to only target certain versions of browsers, certain types of browsers, or operating systems. Also, there is what I call the referrer attack, which means the exploits are only served to requests that originate from one of the infected websites. So if you directly analyze, it will do nothing. Only if you come from one of the infected websites they know they have. Also, there are some real-life examples when the attacker doesn't target the user the first time he accesses the page, but rather it will attack him on revisiting, like when he opens a link on a secondary page of the website, etc. So why not using an existing solution? Existing solutions make use of honey clients, but feeding every URL to a honey client is very time consuming. We saw earlier how long it would take us to do this. Publicly available honey clients, as you've seen before, have no fingerprints, which could lead to detection evasion by the attacker, by the malicious JavaScript. Also, our solution has to be quite scalable, quite large, because we have a lot of data to process, and no publicly available solution can scale to our needs. This means that we have to distinguish clearly between benign and malign URLs pre-sandbox analysis. So, the first steps we took was to understand the inner works and dynamics of malicious JavaScript. So we analyzed like 40 different malicious JavaScript samples found in the wild. Sorry. We found that they share a certain set of common features. So we were able to compile a heuristic set from the extracted features. Then we created an artificial intelligence model using the heuristic set to be used in our anomaly detection engine. This is the solution. Here you have the internet. This is the list or the database feeding websites to our agents. The agents scroll the internet, and for every website, they analyze every page, every script to see certain features. Everything is sent to a message broker, which sends everything to an anomaly detection engine, which then sends the maliciously flagged URLs to one of our two sandboxes. One it's a Node.js sandbox. The other one uses Intel VTX virtualization methods. This is the reporting part where the analysis and all the results are correlated. If there is a problem with any discrepancies or stuff like this, all the URLs are submitted for manual analysis. So basically, our malicious JavaScript detection engine was written in C and assembly. It was multi-threaded analysis because we had to be very, very fast. It crawls a list of websites analyzing every script found on every page using heuristic techniques. It searches the HTML code for suspicious JavaScript methods and correlations between them. We call them features. And also we look for different evasion techniques inside the script code, because sometimes there are certain scripts who are interpreted in one way by one browser and totally different by a different browser. So basically, if they were to target a single type of browsers, they would choose to only make code that would execute for that certain type of browser. We have a smart scoring system in the way that we contextualize the code. For instance, the same method is getting scored differently depending how it is correlated with the rest of the code. So basically, there are these are the set of features a malicious JavaScript shares. This is the first, the most important. It has to silently redirect the user to the exploit site. The second thing is the obfuscation, in order to evade signature detection of the attack. Selective execution is the third feature. Delayed execution is the fourth feature. And here they are. What is obfuscation? Obfuscation is the obscuring of intended meaning in communication, making the message confusing, willfully ambiguous, or harder to understand. This is again our example of obfuscated code. This is how it looks, totally awful. But we can extract some very important snippets of information from this. When we deobfuscate this code, we see that they create the silent redirection in this part. They have the user agent check here, so only if it's an Internet Explorer, Opera, Web TV, or Windows, it will be exploited. Here we have the delayed execution method I was mentioning earlier. You see, they create a function that gets executed after 1 second, so that maybe to deter the analysis by sandboxes, they decided to execute after 1 second. So our feature set basically consists of signs of obfuscation, which can be cycling features like instructions like while or for, transformation features inside and outside cycles, like replace, parse int from char code, unescape, etc. And execution features, namely eval. Also, we're looking for redirection features like HTML elements, meta redirect tags, Java, iframe, JavaScript, etc., etc., etc. It's a whole lot of redirection features we're analyzing for. Also, we're looking for unusually large variable content, unusually large eval content, unusually large unescape content, delayed execution instructions, occurrence of white spaces inside script code, because most, namely all, the JavaScript, the malicious JavaScript samples we analyzed contain like 0 white spaces. Guys were, I guess, they were trying to save space, I don't know. But this is the fact, they use very little white spaces. And also we're looking for signs of concatenations, which we consider to be like more than 2 plus signs in close vicinity. So we ran a banning script through our system. This is the score it got. As you can see here, it have cycling features, it have transformation features, but 0 execution features, 0 redirection features. It has white spaces. So this would not raise any alarms. But as soon as we feed our obfuscated sample of code, we see that cycling features are 40, transformation features are 110. We have execution features, we have redirection features, we have delayed execution, and no white spaces. 0 white spaces, 2 signs of concatenation. Here, if you can see, we have the redirection feature, which is the word iframe inside the script code, which is a very alarming sight, so to say. We also see the set timeout here highlighted, which enables the code to be ran after waiting a certain period of time. We have no large var content inside this script code. So the big data processing for the CNAS, the name of the tool we developed, basically starts multiple agents to analyze a given list of websites. The agent crawls the website and analyzes every URL found. A stream containing the URL name and the score for each URL found on a website is sent to a message broker. The message broker sends data streams to an anomaly detection engine. The anomaly detection engine uses a random forest machine learning algorithm. If anomaly detection engine sees an anomaly, the URL who triggered it is sent to the Node.js and VM sandboxes in parallel. If anomaly detection was triggered and neither sandbox reported suspicious behavior, the HTML page along with the affecting scripts are submitted for manual analysis, because we want no false positives and no false negatives. All the results are output to a NoSQL database. So our anomaly detection engine uses a random forest regression algorithm. Random forests are one of the most successful machine learning models for classification and regression, because they combine many decision trees in order to reduce the risk of overfitting. Also, they do not require feature scaling. This means that we can add an unlimited set of features to our anomaly detection engine and AI model. Also, which is very important, they are able to capture nonlinearities and feature interactions, like how these features react in the context of similar presented features in the analyze, so to say. Also, random forest train a set of decision trees separately, so the training can be done in parallel for added speed. The algorithm injects randomness into the training process so that each decision tree is a bit different. Combining the predictions from each tree reduces the variance of the predictions, improving the performance on test data. The Node.js sandbox, we crafted it very carefully. It runs in a contained environment. It performs static and dynamic analysis of emulated code. It feeds the deobfuscated code to DefCamp's malicious JS detection and scoring system. Executes the JavaScript, taking care of certain anti-analysis tricks. It follows redirections. It tries to download the binary, and from this point we perform. We can safely say there are enough signs. It was a drive-by attack, and the downloaded binary can be further analyzed by a manual analyst or a human analyst or something like this. The VTX sandbox makes use of Intel virtualization technology. It's something done from scratch. Each URL is analyzed by multiple VM in parallel. Each virtual machine running different versions of browsers and different type of browsers and different type of operating systems in order to understand how the code is reacting according to the changes and maybe what browsers it and the operating system it targets. Also, every instance uses custom screen sizes generated randomly on the fly, so that the attacker doesn't see that we have predefined screen sizes, so they don't know if we are a human operator or a virtual machine analyzing the the code. Also, it waits for anomalous behavior longer than 120 seconds. We have two minutes when we wait to see if the code does something malicious or not. Also, it emulates mouse movement and clicks in order to defeat the evasion techniques presented earlier, and monitors all the system functions, not only some. Everything everything that is happening in the operating system after the URL is accessed, including all the functions accessed, are reported, and they try to understand if the behavior was malicious or it was a false alarm, or it needs to be manually analyzed. Also, it tracks changes in web pages analyzed to see differences made by the attacker, to extract new technologies of attack and methods used currently in the wild to infect unsuspecting users. This was my presentation. Thank you all. Thank you.
Any questions?
How do you find the URLs of the websites that you then analyze?
We have a feed. We have a partnership with the Romanian organization that gives URLs and takes care of domain names, etc. And we partnership with them. Thank you.
Hello. I am curious about the precision recall score. You mentioned that you have an anomaly detection module there, and you train it with the random forests. I'm curious about the score of precision recall.
Sorry?
About the score of precision recall.
Scoring precision is continuously analyzed. We normally don't have false negatives from our test data, so to say, but we're constantly upgrading and updating our engine. So There will be certain situations when we need to adjust the scoring system according to new challenges.
Okay. Another question. I'm curious about if you tried SVM or naive Bayes approach instead of random forest, or why you choose the random forest?
I choose random forest because it was what I needed for regression. I didn't need any, I don't know, fancy analyze and stuff like this. I was only needed to see if certain methods are called inside a JavaScript, and random forest, it was precisely what was needed. Thank you. Thank you.
Most of the common frameworks, the new ones, especially Angular and React, they're basically all of them obfuscated. Do you actually scan all that obfuscated code to see if?
Yeah, we analyze the obfuscated code and we apply a scoring system. Those frameworks you mentioned, based on Node.js, they don't fall on our alerts on anomaly detection or on our scoring system. Sorry? Yeah, we also analyze the base 64, and also we will do this type. The product is in continuous development. Yeah, we're adding every minute, so to say.
Dude,
Oh no.
what do you do with all the malicious URLs that you find?
Classify.
How do you protect people? You identify all these malicious URLs. What do you do with them?
We call Kaspersky and tell them that.
Perfect.
Thank you.
Another question.
The next question: are you using any kind of whitelisting?
No, not whitelisting. We focus on finding a set of methods that are commonly used inside malicious JavaScript, and also correlations between those methods. For instance, if you have a code that has to be deciphered, the obfuscated, unencrypted, etc., it has to run a few cycles and transformations on that code. Even though normal-looking scripts might have this kind of behavior, they do not share the redirection features or the eval features and stuff like this. We don't need to do whitelisting because at some point somebody could identify our whitelist, so to say, and either bypass it or contrary, we can block or misidentify a legitimate script as being malicious.
Yes, I was rather thinking about the scenario where, let's say you scan my website, you find a obfuscated JavaScript over there, you have a manual analyst to look at it, so basically you're kind of spending money on me, and at the end you determine that this particular script is clean. Wouldn't it be more feasible to, let's say, take the SHA hash of the file and to put it in a whitelist table, since you're going with big data?
The database would be rather huge because making a hash of each legitimate script would there are lots of scripts from Google, Facebook, I don't know. Whitelisting all the scripts is an approach I wouldn't take. I rather try to see the behavior of certain scripts. You know what I mean?
Yeah.
Because I never like whitelisting.
Okay, thanks.